Electricity topic number 2. Again, take out your notes and we're going to focus on some key topics about our key concepts regarding Coulomb's law. Coulomb's law is looking at the relationship between charge size and also the distance charges are away from each other. So it's really building on the idea of electric fields, so some things that we've already talked about. So we've drawn some diagrams about electric fields. So now we're just going to look at it mathematically in terms of that relationship. So it was developed by Charles Coulomb, and again, I'm never going to ask you for the date he was born and when he died, and the only thing you really have to focus on here is what Coulomb, and that's the charge, right? That's going to be we're going to be using capital C, and capital C is after his last name because he's the one that looked at the quantity of that charge. So the first relationship he looked at is looking at F, which is force, and then he's looking at Q1 and Q2, and now Q is equal to charge. And that's the quantity of charge. So the greater the charge, so for example, if we had 2 coulombs of charge versus say 4 coulombs of charge, 4 is going to be twice as strong. So think of a magnet, it would be like twice as strong in a magnet or twice as strong as an electrical charge as 2 coulombs. So Coulomb represents charge, so the Q is representing really the product of those two charges. And that relationship is just looking at the size of the charge. So if I increase Q1, or increase Q2, the force of attraction or repulsion, so that force can be either, so it's an attraction or a repulsion, will increase. So you can either change one of the charges, so either Q1 or Q2, or you can change both of those charges. In either state, if you look at that relationship, because you multiply them, then that means that it is directly proportional. So that means that as you increase the charge, you're going to increase that force of attraction or repulsion. And again, if you think about a magnet, it's the same thing that happens in a magnet. If I increase the strength of the magnet, then that force of attraction or repulsion is going to be greater, whether I increase both of the magnets or if I just increase one of the magnets. So it's the same idea with an electric charge. Now the other relationship he looked at was the distance. So here, again, this symbol means proportional. So this means that we are inversely proportional to the distance. And this is a huge factor. It's a greater factor than actually the charge because we are squaring that, so it's an exponential relationship. So that exponential relationship between force and distance has a huge impact on attractive and repulsive forces. So again, when we looked at the charge, so if I looked at a positive charge, and as I move away, right, we had our field diagram. This is where those density of lines comes into play. Just like, again, like it would be in sound. So if I look at the area, again, just right next to the charge, again, I have more lines per unit area, so I'm going to have a really strong force of attraction or repulsion. As I move further out, so if I go out to where the arrow tips are, I have less lines per unit area. The intensity drops off, in this case, exponentially. So the distance has a huge impact. And again, you would find that, again, if we use the same example as a magnet, you can bring a north and south end of a magnet close to each other, and it doesn't seem like anything's happening, and then suddenly you get into a very close proximity, and suddenly the two ends will either repel or they will attract, depending on whether you're using two norths, two souths, or a north and a south. And that's because distance has such a huge impact. So Coulomb really examined that relationship. And so what he found is the size of the charge, right, increases the amount of force of attraction and repulsion, and the distance has an inverse relationship, which means the further we go apart, the greater the impact of the force. So the less force you get, and again, that can be a force of attraction or repulsion. So the final relationship he comes up with is force equals, and then at the numerator you have your Q1 and your Q2. Now, again, those are your charges, and then you'll see that suddenly you have this K. Well, K is a proportionality constant, and it's actually going to be equal to 1 in the conditions that we are always looking at in grade 11. So even though you'll see it in the textbook, and it will actually even outline the same thing we're going to talk about here, is because it's 1, you don't have to actually include it into the equation. If we were working with other conditions, we'd have a different proportionality constant, and that would affect the actual force of attraction and repulsion. But because we are going to keep ours the same, then it is going to be equal to 1. And so you can actually cross that part out and then just deal with the final equation, which is going to be Q1 times Q2 divided by D2. And remember that because it is 1 over D2, that's an inverse relationship, and because it has an exponent, it's an exponential relationship. So it has a large impact on that force of attraction and repulsion. Now, when we talk about charge, we have to actually quantify the charge because we've just been calling it Q so far. And so we come up with what's called a fundamental charge, or also called elementary charge. Those charges are really looking at the charge of one electron. So that one electron, which is the 1e here, 1e is equivalent to that 1.602 times 10 to the negative 19 coulombs. And it is a charge that was discovered by what was called the Millikan experiments, which I will review very briefly in a minute. This charge itself, because it's dealing with one specific electron, is not very helpful, because when we talk about electricity, we look at very, very large amounts of electrons. And so we take this number, and we're going to take that, and we're going to go 1 divided by 1.602 times 10 to the 19 electrons. Coulombs. And that's going to find what 1 coulomb of charge is, which is what this number comes to. And this is the number we're always going to be looking at. And this is kind of like a set number. This is a number like the mole in chemistry, right? This is a set number of electrons. So when we talk about 1 coulomb, which will eventually link to 1 amp of current, 1 coulomb of charge is 6.24 times 10 to the 18 electrons. So it's a whole bunch of electrons stuck together. And that is the general movement that we discuss when we talk about a charge moving through a circuit. And so that number there, again, is similar to the mole in chemistry, kind of a set number of atoms in chemistry. It'd be like saying you had a dozen. We all know a dozen is 12. And so we can have a dozen cars, a dozen donuts, a dozen pencils. We all know that that is going to be 12. So when we say we have a coulomb of charge, we know in physics that that's 6.24 times 10 to the 18 electrons. All right, so to kind of establish what that one charge on an electron is, to find out eventually the coulomb, there was a set of experiments done by Millikan, and Millikan looked at trying to find what, again, was called that fundamental charge, and then Coulomb then helped using that information to come up with what 1 coulomb of charge would be. So what Millikan did, and again, you have to appreciate the time period, and this is centuries ago or a century ago, and they don't have the equipment that we have in our labs today, so they had to come up with a design in order to establish what 1 electron was. So they had to not only figure out how they're going to do it, but then they had to actually build the equipment to do it and then analyze that information. So not only did they have to think outside the box on how to design it, but then they had to use some creativity and building skills and actually to establish the actual apparatus to use. So basically, in this experiment, an atomizer is kind of like a perfume bottle, like a fancy perfume bottle, like you would spray, and it comes out kind of in a fine mist. In here, he had oil, and it would spray out, and the oil would then fall through this little hole, and as it fell through the hole, it would rub against the outside edges of that hole. And then we know by charging by friction, we can have electrons jump onto that. Just like if you rubbed a balloon in your hair, and that balloon in your hair, you get electrons from your hair to the balloon. And then that's what gives you that charge. So the charge on the oil droplet was unknown. And so they didn't know if there was 1,000 electrons jumping on it, or 1 electron, or 20 electrons. All they knew was that as it went through that hole, it would gather some electrons. Now, it would continue on down, and the first couple of times that he did it, I shouldn't say a couple times, the many times he did it, he would use a telescope and he would examine those oil droplets coming down, and there would be a little, behind that telescope, there's actually a grid, and he would see the oil droplet going down through that grid, and through some basic kinematics, he figured out what that terminal velocity was of that oil droplet. And in finding out that terminal velocity, he could figure out the kinetic energy, and then he could then find out the mass of the drop. So then he would know the force that drop was exerting, or the force of gravity that's being exerted on that drop. And so he did that, so that was one of the first things he did. So then he figured out, okay, well, he knew the mass of the oil droplets coming through, and once he figured that out, then he could use a battery, and he would create charged plates above and below where the oil was being dropped through. At the same time, this area here, which is not shown in the diagram, he would fire X-rays through it. And what the X-rays would do is that they would take the oil droplet, so the oil droplet is kind of a blown up spot on it, so you'd have the electrons sitting on the oil droplet, and the X-rays then would ensure that the electrons stayed on that oil droplet. And so as it dropped down, what he would do is he would change, again, this is a switch or a variable resistor, and he would change the resistance level, which would change the amount of voltage going through those two plates, and he would change it to the point where the oil droplet would just stay suspended in the middle of the air. And then he would record that charge, whatever that charge was, and then he started recording all that data. And what he found was, over the thousands and thousands of times he did it, that it always went up by the same multiplier. And that multiplier is that 1.602 times 10 to the negative 19 coulombs of charge to suspend it. And so it went up by that multiplier because every electron that was added had that same specific charge. So then he used that information then to figure and work with Coulomb to figure out what 1 coulomb of charge would be. Again, really, it's more of an appreciation of this whole mechanism. You know, the science that had to go behind that to figure out what that electron was, and it's still today when they redo that lab or when they do that experiment, they get the exactly same results he did. And so that is how that fundamental charge was discovered. And so that's really it for topic number 2. So it's really, you're looking at the relationship between the size of the charge and force, the distance and force, which is an inverse relationship, and then now we know what 1 charge is, and 1 charge is 6.24 times 10 to the 18 electrons.